Welcome to EC Elimu Learning Simplified, and welcome to this lesson. Today we are going to discuss the mirror formula, and this is a very important formula because it relates three quantities that we mostly use in curved surfaces and other optical instruments. That is the focal length. It also related to the U, that is the object distance, and V, that is the image distance. This formula is a very universal formula in optics in general, because when we move to Form 4 thin lenses, we will use it as a mirror formula. It will be the same formula. Then now after high school, you will discuss it at higher level physics, where you will discuss what we call the physical optics. My name is Albert. I hope you will enjoy the lesson. By the end of this lesson, I expect you to be able to describe how a mirror formula relates the focal length, the image distance, and the object distance. Then we will discuss what we call the real is positive convention in mirror formulas. Then later we will discuss few examples involving a mirror formula. So the mirror formula relates three important quantities, that is the object distance U, the focal length F, and the image distance V. So like in this case, if you have the two mirrors that we have discussed here, if we can start with the concave mirror, a concave mirror is represented by a symbol like this one here. Then we have a focal length or a focal point in front. Then we have the center of curvature in front of this mirror where we have the pole. So this one is a concave. Then now if we have a convex mirror, for a convex mirror, we have a representation like this one here. This is a convex mirror. Let me use a very different ink. So if you have it being represented like this one here with curve like that, so this one is a convex. Then in this case, remember what we said, the convex mirror has F behind this reflecting surface and also C behind the reflecting surface. So in this case, if you have an object at this point, let me draw an object very fast. If you have an object at this point here, then in this case, this is the object. We're going to draw two rays which will form the image on this object for a concave mirror. A ray parallel to the principal axis will be reflected along F, and it will look like this. So that is the first ray. Then the second ray, we can draw a ray which is perpendicular or which forms an angle to the principal axis, and it will follow the laws of reflection. Like in this case, if this is I, I'm just approximating, then it will form a same angle as the angle of reflection, and then we will have our image formed at this point here where these two rays meet. So we'll have our image formed at this point here. This is the image. Then if we, and this is the object. Then now if we have an object down here, if we have an object on this convex mirror, then we can use the two rays that we discussed. The first ray is a ray which is parallel to the principal axis. This ray will appear to have been emerged from the point F. So in this case, if I can draw that, it will appear to have emerged from this point here. Since it appears and it's not real emerging from that point, we draw dotted lines, then this ray will be reflected like that. Then another ray that we can use is a ray from the tip through C, or appearing to come from C. This ray will be reflected along its own path. So in this case, it will be virtual behind there. So this one will be reflected to the mirror and then back on its own path. So in this case, we will have our image which is virtual at this point. So if now we can label them, this is the image, and then this is the object. Then this one here is the image, this is the object. Now, if we measure the distance from the object to the mirror, this one here, for this case here, for a convex mirror, this is our image distance, that is V. Then object distance is the distance of the object to the mirror. In this case, this is our U. And now, if you have the concave mirror up here and you want to measure the distance of the object to the mirror, in this case, it will be this distance here. Object is there, then to the mirror, this one here, this is our U, and then the object or the image distance from the mirror, we can have it as this one here. This is our V. Now, if you know the focal length here as F, in this case, our F is here, then here we have our F there. So we can relate U, that is the object distance, the distance from the object to the mirror, and V, the distance from the image to the mirror, in either mirror, either concave or convex, as 1 over focal length is equals to the 1 over object distance plus 1 over the image distance. And then now when you represent it like this, F represents the focal length, U represents the object distance, then V represents the image distance. Then from this one, now that's what we call a mirror formula. So a mirror formula is 1 over F is equals to 1 over U plus 1 over V. So real is positive sign convention is a sign convention used with mirror formula in order to determine the position and the nature of the image formed by a curved mirror. According to this real is positive sign convention, all distances are measured from the mirror as the origin. If you have to measure U, that is the object distance, you have to measure it relative to the mirror. If you have to measure the image distance V, you have to measure it relative to the mirror. And then if you have to measure the focal length, you have to measure it relative to the mirror. Then another important thing under this real is positive sign convention is that the distance of the real objects and the images are considered to be positive. Like in this case, if you have an object in front of a mirror, then that U is positive. Then if you have V, that is the distance of all the images formed in front of the mirror, it means V is also positive. And then the focal length for a concave mirror in this case is also positive because it's always in front of the mirror. So for a concave mirror, if we write our mirror formula as 1 over F is equals to 1 over V plus 1 over U, F is always in front of the mirror, so it is positive. V can depend on where you place the object. If the object is between the pole and the focal length, or at the focal point, then that V will be negative. But otherwise, V is positive. So I will not indicate that here because it depends on the position of the object. Then U is always positive because an object must be placed in front of the mirror. Then now, distances of virtual objects and virtual images are considered to be negative. In this case, if you have a convex, and this one is mostly always under a convex mirror, a convex mirror, if you write the mirror formula as 1 over F is equals to 1 over V plus 1 over U. In this case, remember, for a convex mirror, the focal length or the focal point is behind the mirror. Therefore, F is negative always. And then we said for a convex mirror, images are always formed behind the mirror. So therefore, V is negative. And then U is always positive because an object is placed in front of a mirror. So in this case, if you use a mirror formula and you get a negative F, then it means the mirror you are using is a convex mirror. It's only a convex mirror which has a negative focal length, which is behind the mirror. If you use a mirror formula and you get V as a negative, it means you are using either a convex mirror, which always forms images behind the mirror, or you are using a concave mirror where the object is placed between V, F, and P. So if you are told that you are using a concave mirror and you get V as a negative, then automatically it means the object is in between P and F. Otherwise, if you are using a convex mirror or if you are using a mirror and you get V as a negative, then the mirror that you are using is a convex. So the first question, an object is placed 10 centimeters in front of a concave mirror of focal length 20 centimeter. Determine the position and the nature of the image that is formed. First thing that you do, you identify what you have. In this case, we have U, that is the object placed in front of a mirror, 10 centimeter. And then of a concave mirror, concave is very important here because it's going to help us to know the formula that we're going to write in terms of sign convention. Of focal length 20 centimeter, focal length 20 centimeter, F is equals to 20 centimeter. Then determine the position and the nature of the image formed. So we are going to determine V, that is what you are going to look for, and then the nature of the image that is formed. Now, without even doing a calculation, we can even predict where the image will be formed. In this case, look at this. The object is placed 10 centimeter in front of a mirror whose focal length is 20 centimeter. So if this is a concave mirror, we have F here and we have C here. This is 20. The object is placed somewhere here, 10 centimeter. So this object is in between F and P. And what do you know about objects placed between F and P for a concave mirror? The image will be formed behind the mirror. So we expect what we will get here is an image which is formed behind the mirror. But let's now do a calculation to confirm if we can get an image which is formed behind the mirror. In this case, V should be negative. That's what we expect. So if we can now use our mirror formula, 1 over F is equals to 1 over V plus 1 over U, then in this case, our F, since this is a concave mirror, is positive, then it's going to be 1 over 20 centimeter is equals to 1 over V plus 1 over U, which is U is 10 centimeter. Now, we will bring like terms together. This we bring in the other side. Then if we do that, we will remain with 1 over V is equals to 1 over 20 centimeter minus, when it comes, it will become a minus 1 over 10 centimeter. Then now we can get an LCM for this, and it will give us an LCM is 20. 20 divided by 20, 1 times 1, 1 minus 20 divided by 10, 2 times 1, that is 2. So in this case, it will be per centimeter. So if now we solve that one, it will be 1 over V is equals to 1 minus 2, negative 1 over 20 centimeter. And now if we solve this one by cross multiplication, it will be 1 times 20 centimeter is equals to V times negative 1. Then in this case, for us to get V, then we will divide by negative 1 on both sides. Negative 1 on both sides. Then now our V is going to be 1 times 20 centimeter divided by negative 1, which is in this case is going to give us V is equals to 20 divided by negative 1 is going to be negative 20 centimeter. So as you can see, what we have got V, the distance of the image from the mirror is negative 20. It means it's behind the mirror. And now if we can give the characteristic of this image is that the image is virtual. It's virtual because of a negative. So you have to give a reason. V is negative. Then this image is magnified. This image is magnified. It's magnified because V is large than U, because magnification is V over U. Therefore, if V is larger than U, then it means the image is magnified. Here, V is 20, U is 10. And this image is also formed behind the mirror. You can give that as a characteristics, and that is all. So the second question reads, an object placed 10 centimeter from a concave mirror is magnified 3 times. Calculate the focal length of the mirror. So in this case, we have to write down what we have. The first thing we have is an object distance U as 10 centimeter. Then we have magnification as 3. Remember, it does not have unit, it's a ratio. Then in this case, they are asking us to find F, but we cannot find F from the mirror formula. Remember, it's 1 over F is equals to 1 over U plus 1 over V. Therefore, it means we only have U, we are lacking V. But can we find V? Yes, we can get it from magnification is equals to V over U. In this case, magnification is 3 is equals to V, which you are looking for, divided by U, which is 10 centimeter. Therefore, here it will be V is equals to 10 times that times 3, which is 30 centimeter. So we have V also as 30 centimeter. And in this case, if we take this to the mirror formula, it will be 1 over V, 1 over F, because we are using a concave mirror, F is positive, is equals to 1 over U, that is 1 over 10, plus 1 over V, that is 1 over 30. Then in this case, 1 over 30. Then here, remember it's centimeter, centimeter. And now what we do for us to get 1 over F, we're going to get the LCM of 10 and 30. And that is 30. 30 divided by 10 is 3 times 1 is 3. Then plus 30 divided by 30 is 1 times 1 is 1. Then this one, what we are going to get is per centimeter, which if we solve, it will be 1 over F is equals to 4 divided by 30 centimeter down here. So in this case, if we want to solve this, we can cross multiply. Then it's going to be F times 4 is equals to 1 times 30 centimeter. Then here is going to have divided by 4, then now our this 4 will go, we'll remain with F as 30 divided by 4, which is in this case going to give us 7.5. So our focal point, all focal length is 7.5 centimeter. So that will be the focal length. So the last question, which involves a convex mirror, the question reads, an object is placed 15 centimeters in front of a convex mirror of focal length 10 centimeter. Calculate the image distance V. So in this case, we have to identify what we have. And what we have here is U, that is the object distance 15 centimeter. Then we have F as 10 centimeter. But again, we also have what we call a convex mirror. That mirror is very important for us to identify what we have. Then the last thing that we are looking for is V. In this case, if we write a mirror formula for a convex mirror using the positive, real is positive sign convention, then it's going to be 1 over negative F, because this is a convex mirror. F is always behind the mirror. Is equals to 1 over V. That's what we are looking for. We don't know if it's positive or negative. Then divided by 1 over U, or plus 1 over U. So in this case, if we substitute with what we have, so where we have F, it should be negative. We represent that it's behind the mirror. So here it will be 1 over negative 10 centimeter is equals to 1 over V plus 1 over U, that is 1 over 15. 1 over 15 centimeter. And in this case, if we take this the other side, then it will be a negative. Then what we will have as our 1 over V is going to be negative 1 over 10 centimeter, plus when it comes to this side, it will become negative 1 over 15 centimeter. So in this case, we will have 1 over V is equals to LCM of 10 and 15 is 30. So in this case, if we have our 30 as our LCM, then now we can solve it. 30 divided by 10 is 3 times negative 1 is negative 3, plus 30 divided by 15 is 2 times negative 1 is negative 2. Then what we will get here is per centimeter. Then now we can solve this as 1 over V is equals to negative 3 plus negative 2, that is negative 5 and then divided by 30 centimeter. And now for us to solve this, we cross multiply. It will be equals to 1 times 30 centimeter is equals to V times -5. So for us to get V, we divide by -5 both sides. So we'll divide here by -5 divided by -5. And now -5 will cancel out on the right hand side. Then we will remain with our V is equals to 30 centimeter divided by -5. It means it will be -6 centimeter. So what you can see here, V is automatically a negative because we said all images formed by convex mirrors are behind the mirror. So this negative tells us that the image is formed behind the mirror, and that is true according to what we know from a convex mirror. Another thing that I want you to note, this is -6 centimeter. This negative means it's the image is virtual or is behind the mirror. Another thing, remember magnification is equal to V over U. In this case, look at V is 15, U is 6. So when the numerator is less than the denominator, it means this image will be diminished or will be smaller than the object. And that is true whenever we have convex mirrors. The images formed by convex mirrors are always smaller than the object height. So that marks the end of our lesson today. In the next lesson, we will discuss more examples involving the mirror formula.